Wordle is a popular online word guessing game. Players have 6 attempts to guess the 5-letter word of the day, and after each guess, they receive a color-coded output. But wait, how is this related to the topic of security? We can think of Wordle as a cryptographic function. The input word is hashed with the answer as the key variable to produce a hash consisting of 5 colored outputs. A green letter is both in the word and in the correct position. A yellow letter is in the word but in the wrong position, and the gray letter isn't in the word at all. The goal of the game is to crack the hash function to find the key variable, which is the same as the answer. We can use the theory of entropy to minimize the number of guesses it takes to win. Entropy is the foundation upon which all cryptographic functions operate. The more entropy the output contains, the more costly it will be to brute force attack it. The entropy of a random variable is the number of bits required to describe it. The information content of choosing from n items is logged to n bits. The list of potential answers for Wordle is visible on the website's source code. The list contains 2,315 words, so 2,315 possibilities for the key variable. Using log2n, the entropy of possible Wordle words is 11 bits, more or less. Every time we guess a word, the game returns a hash, a color-coded feedback consisting of 5 outputs. Each output will be colored one of 3 ways. This means that each guess can potentially have 3 to the power of 5 or 243 different hashes, which using log2n translates to almost 8 bits of information. Let's demonstrate this. Here is a Wordle program I wrote in Python. After each guess, words are eliminated from the list of possible solutions based on the output, and it tells you how many possible answers remain out of the initial 2,315. The first guess is the word Steam, and the feedback received is YY-. This feedback pattern contains roughly 6 bits of information, as it only narrows the possible answers down from 2 to the power 11 to 2 to the power 5. If the answer key was different, the hash produced will also be different. In this case, this output pattern contains --, roughly 3 bits of information, as it narrows the possible answers down from 2 to the power 11 to 2 to the power 8. I ran a Python program that took Steam as a Wordle input and calculated the probability of each of the 243 different possible outputs. The most common output is --, which leaves 286 possible solutions and happens 12.35% of the time. The least common output is G, which leaves only one possible solution and happens roughly 0.04% of the time. Since there are different outputs with different probabilities, we want to choose the input that produces the highest average information output. Shannon's entropy measures the uncertainty of a probability distribution through this formula. Hx is the average bits of information expected to be returned from the input x. P is the probability of a specific outcome, and minus log 2p is the bits of information from an outcome with the probability p. I made a Python program that calculates hx for each word in the list of possible answers. The starting word with the highest hx is race at 5.88 bits. In comparison, the starting word with the lowest hx is mama at 2.27 bits. The program suggests the best guess for each round of Wordle based on hx values of remaining possible answers, which are recalculated each round since the remaining possibilities are reduced after each guess. This is a combination of a dictionary attack and a chosen plaintext attack, as we have access to a dictionary of words as well as their respective hashes. I ran a Python script that plays 100 games of Wordle, each time using the recommended word choice calculated by the entropy formula. The average amount of guesses it takes to crack Wordle is 3.6, but not bad when compared to the human average. For more information, please read my project report. Overall, I am really happy with this project. I started this project with the goal of cracking different ciphers. After experiencing difficulty cracking the substitution ciphers, I ended up playing a Wordle game. If given more time, I would have liked to try cracking more ciphers. I think it's surprising that Wordle, a game seemingly unrelated to security, can be played through crypto analysis. Now I have a working Wordle cracker that I can show off, along with the entropy theory behind how it works.